So, hello, uh, good afternoon, everybody. Welcome to the week 4 problem solving session. And this session, I think, have all gone through assignments, and you can see that most of the assignment questions are numerical based when you compare it with more numerical intensive when you compare it with the last 3 weeks. And you can see that most of these questions are like this Boolean based, Boolean and the gate based system, and these are the gate and these are the system microprocessor system, and these are like flip flops, and yeah, this is again the architecture microprocessor architectural question. These questions, I mean, these are the questions. I mean, for the last 3 years, there's been a question. Sorry, so so I'm talking. So I was telling that this question, I mean, the architecture, the primitive microprocessor architecture. These questions are like repeatedly being asked over the last 3 years. So please, please take this question very seriously, okay? And I will solve one question so that you get an idea how to solve this type of. So just give me a second. So yes, so you can see. So let's start the today's session. So the first question is based on the combinational logic systems. And so basically the and or gate system. So here is the block diagram for this gate system, and you need to solve this question. So the outcome of the combinational circuit is, so the outcome is they want to know what y is when a b c's are given. So a b c's are the input and y is the output, and you can see that this is an and gate, this is a zor gate, and gate, zor gate, okay. Please go over your basics, like what are the different types of gate and what is basically their truth table. Please remember their truth table. So I mean, I'm not asking you to remember every truth table, so you can know and or even zor also, and or zor and not. And after that you can make such a like and NAND and NOR gate. These are these, I mean, you can remember. Okay. So let's start. So how to proceed this type of question? So one way is to use this what I'm one way is to use a truth table. Okay, so what you can do is like you can use 100 and let it know what is y value is there. Okay, and every combination of input you will get some y, and based on this you just check each option which condition is varying, or the other condition is using this arithmetic using arithmetic operations. So basically, so basically first what you need to do is like you just need to simplify the problem. Okay, I think you can see that a b, so it's an AND gate, then it's kind of a multiplication, A dot B, and similarly then B C is B dot C, which is kind of a multiplication. And XOR, when you see XOR gate, there's a different kind of a notation. AB, this is plus encircled or additions encircled. BC is a sign of a XOR, where BC and this AB is the input here, and it is giving like that. And this is XOR gate ABC, and so basically what they, when you do this, then you will get y is equal to this, you will get when you do the simplification, and right. And so how to solve this kind of a question, right? So for this i would uh, I would suggest you to go through this six term called boolean boolean laws. You can search on Google, and you get some basic in laws, like. So this is something I don't want you to by heart this thing. I mean, I don't. I mean, learn by heart. But what you can do is like just get an idea like what kind of laws are following. So AB is can be written as BA, associative laws, distributive laws. So these laws will be helpful in the long run. And there is one more thing called De Morgan law. Uh, which you can which you want to, and uh, there's this formula for XOR gate, which is A XOR B is equal to AB A B complement plus A complement multiplied by B, like that. So so how to solve this kind of a question? So you have this. So you are using some kind of associative property, I think. Am I right? Associative, is it associative? So yeah, I think it is taking some kind of a common associative property. Associative. These are the, so yeah, we are following some associative product. What we have done is like we have taken a common AB from this two blocks, and it is like C or one. Okay, and what is C or one? What you can do is like you can use this formula. I think C or one. So C A complement one complement is zero, right? And then A complement is B complement, right? And B complement it's B, right? So it should be, so multiplied is zero, then it's C complement only. That's why you can see that instead of this writing C complement, then the left one here. And again you can take a B common here and just A or C. And again you can use this formula. Okay, this is this formula. So again I'm using this formula where AC complement is A and C complement is B, and when you use this formula you will get this kind of, again what you can do is like here what we have done here is something like yeah, so here what we have done is, here we have used some De Morgan's law. There is this De Morgan's law. What we have done is like I think this is the law. So what, instead of this part, talking about this part, so we take this as this, and we just so what we are doing is we are converting this second order thing into the first order thing. Like, so this is second order, like one order, second order multiplied the second. So first order. Then if it's multiplied, then it's a second order. That we are dividing it into a second order so that it will be simplifying stuff. Okay, so we can use this stuff and again this stuff. In this manner you can solve this kind of a question, but you need to know the formula. And the other way is, what you can do is like you can make some kind of a truth table, right? And something like A, B and C, and then there is a Y also. Okay, and you can make every combination. So there are three, so like there will be 2 to the power 8, 2 to the power 3, 2 to the 3 combination. There are 8 combination. For 8 combination uh, you can get some value, right? But I think here Y is given or not. If Y is given, then you can do it. But if Y is not, then won't be able to do. So this actually, I'm sorry. So this truth table idea work only when you have some A and B value and some Y value is given. You need to reach some, suppose one value of Y and A, B, C is given, then you can use this kind of a formula. Then coming to the next question. This is the minimum number of flip flop is required in 8-bit counter. So what is minimum number of flip flop? So I think Professor Gandhi has told you what is flip flop. Flip flop is something where you can store, right? So it's like a 1-bit register. So I mean, how? So this is what a flip flop look like. Okay, so this is sorry. So this is one flip flop. Okay, this is another flip flop. Minimum number of flip flop we have used, and this is I think okay, number of flip flop. So here, so 1-bit. How many number of flip flop is required in 8-bit register? This is what the flip flop is. And so here is one flip flop, second flip flop, and third flip flop. So what it do is like it store values, one, store 0 or 1 for one period or one clock cycle. After that, it releases to the second flip flop and similarly to the third flip flop. So what they are asking is minimum number of flip flop is required for 8-bit counter. So 8-bit counter is basically some kind of a register which has, I mean, you count it as a register. So there are like eight registers. So 8-bit counter is basically going from 0 to 2 to the power 8 minus 1, right? For this, you need 8 digits, 8 8 boolean values. Okay, and I've already told you that each flip flop can store one value, right? For storing 8 values, 8 boolean values, we need 8 flip flops, right? Answer will here will be D. Simple question. Okay, so similar, I think if you go to, I would like to say, I think, so if you go to the assignment, there are some questions related to this also. And like how many number of flip flops, how many number of address line is there, then so I will uh, how many data lines. So there's one question related to that. I will discuss with that. But I think last year there were assignments on flip flop also. But please, these are the basics thing. Okay, so this kind of question can be asked in the final exam. So there is a question on timing diagram. Timing diagram. So previously I was talking about combinational logic. I think now I will talk about the sequential logic gates. So these are the D flip flops. I will talk about D flip flops. So these are it's a type of a flip flop. Okay, and these are edge triggered when you're going from a lower edge to a rising edge. So what they're asking is draw the output timing diagram of Q. Okay, so this is your input D. This is your output Q. Okay, for the given input D flip flop. Okay, so what they want is like they have given a clock. So the clock cycle has given here, and here the data. So this data, so this is the input. Input is our data line. So the input is given also. What they want us to know is to draw this timing diagram. Timing diagrams mean you need to again draw something like that, but it will be Q. So the input is given and clock is given, and they want this Q. Okay. So how to approach this problem? So before approaching it, you need to know some basics. Okay, what is this D flip flop? So this D flip flops look like this basically. Okay, so this is input and this is output. And if you read their truth table, so these are input and output. So something like, so when the clock is zero, okay, when the clock is so clock is something like this, right? When the clock is zero, there will be no change in the variable. So I've told you that D flip flop stores value, right? And so when the clock is zero, it store value. So this whatever value input is there in D, it will remain there. It will not pass to Q. Okay. When the clock is 1 year, whatever value which is in I or input will pass on to Q. So in this case, if you see, there is no change when clock is zero. If there is one, if the clock is one, which is I think enabled, then the clock is this part. Then there is the D will become Q. Okay, then this input will become Q. Okay, and similarly, if the data is one instead of zero, then Q will become one. Okay, so it depends on the data. So it can be anything, zero or one. So when the clock is one, then only data will be transferred from the input to the output, which is D to Q. Okay, so this is basic thing. Let's just try to solve this kind of a question. So let's just try this. So these are edge triggered thing. Okay, please remember these are edge triggers. So whenever there is a 0 to 1, then only the clock get triggered. Okay, so let's just try this. So you can see here I have drawn some edges. Okay, and this is a D is input. So let's just say so we need to find out what is Q, which is output, right? So when there is a D is zero, the clock is zero. So no data will transfer. Okay, no data will transfer from D to Q. The Q. So let's just assume the Q default value is zero. Okay. When you see then okay, so then you got there is a D change in value. So there is an increase in value, right? Up to this instant there is a small change in value, right? but it won't change Q because the clock is still not high. The clock is zero here, right? If the clock is zero, then there is a no change. Okay. You see that at this edge, the clock is activated. So at this edge, what is the value of D? It is 1. So the Q is 1, 1, 1. And then you see, then there is a dip. Okay. But the clock will trigger when there is a the D will transfer the value when there is a positive edge. That's what the clock does. Okay. So it goes, it's positive, it's positive, is the value when it also go negative, it means that the clock is zero. So the Q will remain the same. Will be no change, right? Again, you see when you go, the clock get triggered again. It goes from 0 to 1, means that whatever value is in the D, so at this point, D is again 1. So it remain 1, 1, 1, 1, 1. Okay. And you can see that since the clock is 1 here, and again you see the clock get again 0, so will remain that old position, and old position you can see here. Okay. And here the D is 0 here, but it will take that this old position only. Okay. Won't take that position because D is 0. So now here you can see that the clock is again triggered, means it's going from 0 to positive. What's the value at D is 0. So you can see here it's high, it's going down. In this manner you need to solve this kind of a timing diagram. Okay, so there is a question related to that, that's why I'm taking, but I know that it's not in the assignment, but soon you will going to learn this. So there's I mean, this slide is basically for your general information. So you know about the D flip flops, but there is one more thing called SR latches. So latches, there are different types of latches. There are SR latches by NOR gate, so they are using some kind of a NOR gate. So these latches are used for making the D flip flops. So please, why am I doing this? So the thing is, there are two types of latches. Okay, so I think last year there was this problem in the Professor Gandhi sir slides. Uh, all the question Professor Gandhi sir was showing are using this NOR gates. So they are using NOR gate latches. But when the question came in the assignment, the question the gates changed to a NAND gate. Okay, and so what will be the difference in between this? The difference is basically the Q, the output. So you have this S and R input. So you can see that instead of 0 1, it is giving 1 0. So please remember these gates. I mean, not remember this gate, but what you can do is like, you just don't by heart this table. What you can do is, instead of, you can make your you can do the calculation at the examination, and you can, it's a simple table, you can run it. Okay, so you can see 0 0 is memory hold, invalid condition, whereas 1 1 is memory hold, whereas in case of NOR it has invalid state. So this is what I wanted to tell you. Please don't buy hard this. You please always use logics. Okay, and please be careful with the this type of gates. So NOR gate, and this is AND gate. Okay, and the coming to the question. So there is the this question is on sequential circuit. I think I will just use, there's a question on RAM which I will solve. So I think there is one question related to, so this question, which of the following binary output ADC contribute to a 9 volt? These are like basically simple questions. I mean, what you can do is like, they have given 0 0 corresponding is 0 volt, and then at greater value it is given not greater value with value greater than 0.6 the battery voltage. These are basically ADC module, analog to digital converter thing. So what you can do is, in order to solve this kind of a question, you can search on Google. Okay, so there might be some example which can help you to this. I think I have one question related to that, but that will come, I think, in the week 6. Okay, so that's why I can't tell you how to solve this kind of a question, but if you want, I can open that slide also, and I can give you back. But to solve this, you can just convert. You can just Google how to solve this analog to digital, and then you can solve this kind of a problem. Then there is a problem related to, I think, the the capacity of memory in bytes. So these are, and the this address lines and these data lines. So I will tell you, I will solve one problem related to that. So there is this problem. So you can see that the question here is, what will be the size of a memory if there are 32 address line and 62 data word line? So first of all, we need to learn what is this address line and 62. So you all know about this registers, right? So if you stack different register one over another, so if you stack one register, so this is one bit, this is one byte register, which means 8-bit register. So there are eight, eight, uh, eight values or 8 D flip flops are there. Similarly, there are like a different number of registers, and when you combine this whole thing, you get some kind of a memory, right? So this is this is assume this is kind of your memory, or suppose it's a RAM. RAM is a memory chip. Suppose this is your RAM, okay, and it has a capacity of 4-byte memory, right? I think you have read that you have 4 GB RAM or 16 GB RAM. So 16 GB RAM, it means that it has different how many numbers of registers are there, right? That's what. So what they are asking is, what will be the size of memory if there are 32 address lines? Okay. So what is address line? So I think I've told you that I think Professor Gandhi has told you that in each memory there are different registers. So there are 8-bit registers. So there are like infinite number of registers might be there. Okay. I don't know how many numbers of registers are there here, but it is written that there are 32 address line, which means that there are 32 address line. So if we are talking about this register, there have been an address of this register, and there have been an address of this. So when you tell your Microsoft chip to do some operation from this register to this register, you need to first tell them their address. Okay. And I think Professor Gandhi has told you this. So there is this simple question with, I took this picture from Professor Gandhi. So if there are two address like this, okay, there are two address, how many combinations it can make? It can make 0 0 0 1 1 0, and then again 1 1. Okay. So it can address maximum four registers. Okay. So you need to 0 0 0 1. This is 1 0, and this is, so you need to first address them. I'm talking about this address, this register only. So this is what the addressing means. So in this case, it is 32-bit address line. Okay. And here it is four. So there are four registers, and they are given, there are data lines. Okay. So so in this case, there are 8 data lines, which means that there are 8 pins coming out from here. Okay. And this 8 pin will be connected to each of these 8 pins, which means that it's a 8-bit data register, 8-bit register. Okay. Means that it's a 8-bit data. So the each register has a 8-bit register, right? So how to solve this kind of a problem? So in this question, sorry. So if you see this, it is written that it is a 4-byte memory. What do you mean by 4-byte memory? It means that number of register multiplied by their each memory. So I've told you that in address, you have two address, then we can have maximum four registers, right? And each register has a memory size of 8-bit, right? And bit can be changed to 1 byte, right? So it's a 4-byte memory. Simple is that, right? So now how to solve this kind of a question, right? So there are 32 address lines, right? How many combinations it can make? It's like 2 to the power 32, right? And each data line has a 60. So here it's a 16-bit register. What you need to do is just multiply it with it. The 16-bit is 2 byte, and when you multiply it, it's coming out to be like this. So which is 8 GB data. So here answer will be B. Okay. So here in the similar manner, you need to solve this kind of a question like. Sorry, I have not read the question what they are trying to say, but on the similar line only, the concept is basically the same. Okay, and let's just move on to the next question here. So this is how you solve this problem, and there is this problem related to sequential circuit. So this problem will help you to solve this kind of a problem. So this problem, so like not the same problem, but the approach is quite the same. Okay. So there is this the question which is so when the output in the circuit, so this is the output here. Okay, the circuit is 1, it should implies that the data has changed from 0 to 1. Okay, so you have this output, right? What you need to do is you need to take this VA and B, and you need to calculate AB is equal to Y, and this AB is connected to this D flip flop 1 and D flip flop. So let's just say this is 1 and this is 2. There are two flip flops and this is data. Okay, and this is clock. So I mean, we all know that data changes at every time, right? So we need to calculate what is the when the output, when it is Y is 1, how the data is changing. It is going from 0 to 1 or 1 to 0, or change in either direction, or it's not change. It can be A or B, or can be not change. So that's what they are asking, how to approach this kind of a problem. So for this problem, you need to, like, first of all, make the arithmetic diagram, arithmetic Boolean diagram. So this is how you do this. Okay, so you have this. So here I am considering this is A data register and this is B data register, D flip flops. Okay, and you have done this. Okay, this is how you calculate. So how to solve this problem? So this problem can be uh, solved by a Boolean. How Boolean thing? Because you have this one. Okay, so you can draw a Boolean diagram of Y, and you can check when you change this data from 0 to 1, what how it like to do. So first of all, let's draw this Boolean diagram. So so what I'm drawing is, this is the first clock cycle, and this is second clock cycle. So this is the initial default data. This is the initial data when there is no clock cycle. Okay, so let's just assume that QA is the output value of this, A register, and QB is the output value of this, right? And in the first clock cycle, which is when the clock is positive, and when the clock goes positive, okay, the data is D1, right? And when the clock is positive, then the data then the D1 will be transferred to Q, right, which I've told you. So D1, then the QA is D1. But if you see that the same clock cycle is followed by this one, but you see in the first clock cycle, the data will transfer to this one. Okay, the first clock cycle, there will be only transfer of data, which is this one, E1. Okay, so this is the first clock cycle. Okay, then coming to the second clock cycle, in the second clock cycle, the data is D2. Okay, so we wanted to know what is the D1. Is it D1 is 0 or D2 is 1? That is what we want to know, right? Uh, because it is changing from 0 to 1, that after each clock cycle, how the data is changing. That's what we want to know. The first clock cycle is D1, and this is, so let's just say D2. In the second clock cycle, we are giving a data D2. Okay, then the QA will become D2, right? Okay, and what will be the data at this D flip flop? Flip flop, what will be the data? So you can see that at so here it's the Q1 is A. So QB, I think is QB here. QB is 1. How it is 1? So QA initially QA is 1 0, right? And this is QA complement, then it is 1. So at first clock cycle, this will be transferred to one, right? The same. So they are using the same clock cycle. Okay. Then QB in the when the first clock cycle activate, then this data will be transferred to one, right? That is what how you do it, right? This QB. So let's just say this is what we get, and in the second clock cycle we have D2, which is data 2. Then data 2 will become, then in this case when the second clock cycle start, the first data which is D1, the first data which is D1 will be transferred to this data, right? How it goes. This is D1. So when the second clock cycle will start, the first clock cycle, this is D1, right? And this D1 is there. The second clock cycle, what will happen is it will remove that D1 data, and it will make this new data which is D2. Now Q2 QA is D2, right? And what will be QB? So the QB will be D1 dash. Okay, because QB is like the old. This is QB. So I'm talking about QB. So this part I'm talking about. Why it is D1 dash? Because the data which was 0 back then, now it is D1, right? Then it's the complement of 0 complement is 1, right? Then D1 complement is it. So like it is like in a sequential manner it is moving, right? That's what the sequential circuit is. So you have this value, right? So what will be D QB? QB is D1 dash, and QA is D1, right? This is Q1 is D1. So this is how you get. QA is present data, and this is the complement of previous data. This is what you get. So QA is the present data, which is D2, right? And complement QB is the previous data, which is D1 complement. And when you use this formula, is this one, right? And when you use this, these are two things, right? And what you need to do is like now you need to guess. It is D2 and it is D1 dash. What will be, so this is D2 and D1. So how, so what will be your option? So let's say it's changing from 0 to 1. It means that D1 is 0, 0 complement, and D2 is 1, right? Is it make sense? It's 1.1.1, which is 1. So yeah, it's giving 1, right? So I think A is the right option. Let's also check B. So D2 and this is D1, right? So if you see D1 is here, D1 here is 1, right? 1 complement, and then there is D2. D2 is 0. 0.0 is 0. So it's giving 0. So this is wrong actually. C is also wrong, and it is changing. So this is also wrong. So your answer will be A here. Yeah, I think it will remain as it is. So let's just focus this question. So this is the main question. Okay. So please do 33. So please do take this question very seriously. Okay. Because every year this type of questions are being asked every year. Okay. So I will explain it. If you have any doubt, please let me know in the comment section, or you can ask your question in use your what is the forum. You can use the forum. Okay. So yeah, so they have given this architecture diagram of the microcontroller. Right? It's a primitive microcontroller. I think where is the primitive microcontroller you have. So you can see here, this is your chip. This is your memory, uh, mem- uh, the memory block, right? Where, right? This is the memory block, and this is basically your peripherals, basically. So you have this memory chip, and then there is a kind of a board is there, right, where all these peripheral chips are there. So this is the memory chip. So this is the memory chip, and this is kind of a address line. is MA. MA is, I think, what is MA? It's a memory address, right? It's a memory address line. So when it, and what is WR? WR is write. OE is output enabled. Okay, when this is high, then all the data which is inside the MA be send or will be sent out, and this is write, or all the data which is coming inside this register will be written. This is WR and OE functions are, and there are different types of registers. All this is ALU. ALU is arithmetic logic unit. So basically, this registers are used to add stuff or multiply stuff. Basically, do the arithmetic calculations. And then there's a decoder, which, I mean, decoder is basically the opposite of this memory address. It's like decode stuff, and this is IR. IR, I think, instruction registers. And then there is a PC. PC is a program counter. It counts. It increases one by one. There is this count. When this count is enabled, then it will add stuff. And this is the chip. I think chip enabled something. CS. I don't what is it, but yeah, this is how. And these are your inputs which you can give: S1, S2, S3, and this is the basic introduction. And let's just move on to the question. For all questions, content of registers are given. So the values of these registers are given here. All in decimal representation. A is 05, B is 07. So so each register value has been given here. At address 01, the memory holds a value of 0. So memory address is 01. When memory address is 01, what it will do, it will select some kind of a small register. So there are 01 address, so it will select some address here, okay? And there are different types of registers. So at 01 address, there is some register which hold a value of 04. That is what memory address, it means that. And currently MA is 01. So now this whole thing, now this whole memory is holding a value of 04. That is what I'm want to say. And then at address C, this will hold a different value. Let's just move on to the question. So the question is, if the signal S2 is made high, there are different signal, right? S2 is made high in a clock cycle, followed by S1 going high. So then first it is going, first S2 go high, and then S1 go high, right? Then these which of the following is correct? That is what they wanted to know. So how to solve this kind of question? So first, what you need to do is, first you need to encircle or find out the signals S2 and S1. So first we will search for S2 signal here. There is this S2 here, okay? Then there is again, let's say, where is the S2, 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 S2. Uh, this is S2, then this is S2, okay, and we have another S2. So we have another S2 here. This is S2, and I think we don't have any. There are three S2. Okay, so let's see what will happen when S2 goes high, right? And we know that MA is 01, which means that the currently your memory is holding a value of 04. Okay, and this is, I think, a NOR gate. Okay, okay, so which means that these are 0. Then I think it will be enabled. It will enable the chip when S2 is on, which means that it will put this 04 value in the data bus. Okay, now the data bus is having a value of 04. Okay, and let's see what happened here. So you need to only concentrate on those where S2 is going high, right? We don't concentrate on this one because there is no S2 here, and there is here S2. So let's see if this is S2. This is going high. This is right chip is on. So IR data. So IR is he holding any value here? I think IR. So we don't have any value at IR. So we have a 04 value, right, at the data bus, and this is kind of a unidirectional chip. So the 04 value is coming here, but IR is having its own value, right? But when S2 is high, it will write the value which is currently on the bus or the data on the data bus. Okay. So currently it is having a 04 value and S2 is on, which means that IR value changed to 04. Okay. So there is a value, it is written here, but let's see. So now IR value changed to 04 because it is written on it because S2 is on. Let's hope this register. So this is a PC register, which is program counter, which means that if S2 is on, this is on. Okay, and this is some kind of a bi-directional thing. Okay. So data can come inside also, data can go out also. Okay. And write is low, which means that you can't write anything in this register, but output, let's see where is the output. Okay. So there is output enabled, that's one. Okay, so S1 is there, but S1 is the next one. So if S2 is on, it is connected to count. Okay, means that if S2 is on, whatever value which is inside it, I think so now it is holding a value of 04, right? Because the data bus is high. Because S2 is high. S2 is high, right? Whatever value which is in it, it will add one thing. Okay, so if it is a 04, then it will add one, and it will make it 05. Okay. Okay, it will make 05. Okay, it make 05. Okay, and yeah, it will make 05. So now PC will be having 05, right? Now PC register is holding a value of 05, I think. Yeah, I think S2 is high. Then so this is what everything happens. Now let's move on to S1. Okay, when S1 goes high, first look into where our S1s are there. So here is S1 is there. Okay, then is there any more S1 here? There any S1? We have S1. S1. This is one more S1 here, which can. Okay, again S1. Let's see, is there any more S1? So we have two S1. Yeah, I think we have two S1. That's enough. Okay, we have two S1 data, right? So let's say if S1 goes high, which means that output enabled. So it will send the data in this loop also. In this loop only, I think. Output enabled. Yeah. So it will send the data. So previously it was 04. I think it will be 05. It is output enabled. And first let's see what is happening here. If it is S1, then this memory chip will change, will be enabled. Okay, and what will happen, right? I think something thing is missing. So for its count or it rate is high, and okay, there's one mistake which I've did, I think. There's something which is given here. I have not taken it. So if you see PC, initially it hold a value of 02. Okay, so when S1 goes high, when S2 goes high, PC has 02, not 04. Okay, 04 will enter only. I think right is on. Okay, right is always low, so no value can be written here. No value can be written because right is low. We can't write any value. So PC is 02 initially. Okay, what we are doing is S2 is on, S2 is high, which means that its value increases to 02 plus 1. it will be 0 3. Okay, not 0 5. So now PC hold a value of 0 3. That's what I'm saying, not 0 5, right? So it is 0 3. Now what happened? S1 goes high. S1 goes high, which means that it will output the data. So the same data bus will be used to output the data. So now the data bus will have 0 3, right? It's 0 3. Now it is 0 3, right? Because S1 is here. So it will, now the data bus will have 0 3, not 0 4. Okay, because it's changed the value, because this is a bidirectional data bus. And you can see this data can go here, and it can go to this memory chip, right? A memory chip now will be 0 3. Previously it was 0 1, but now it is 0 3 because the data came here. Because why data directly came here? Because output is always high. Whatever data will be there, it will come here. Sorry, output is no, because output is high, but you see S1, we made S1 high, right? So when we made S1 high, whatever data is in this data bus, it is written on this MA. So now it is 0 3. So MA is 0 3. When MA is 0 3, the value of a chip memory is 0 8. Now then it will go to 0 8. Okay, the chip is 0 8 now, and it is always on. Okay, so no, it's not on 0 because there is no S1 here. Now the memory value will be 0 8. Okay, and so the now the memory value will be, so C option is right here. Higher register, so I have told you higher register will hold a value of 0 4 because it was written here, because S2 was on, right? And the PC register will be updated to 0 3. So the PC will be 0 3. So this is also right, this is also right, this is also right. And T register, what is T register? So we don't have any signal via T register, so A and B is wrong here. So in this manner, you need to solve this kind of a problem. And there's one more problem which I have shown you. Let's see the time here. I think it's 47 minutes, but I will take one question. But uh, I think this is a simple problem. So you want to guess what is the gate. So let's just try to read the question. So we wish to construct a counter. The counter number is 1 2 3 4. So there is a counter which can measure 1 2 3 4 and then reset to 1. So you all know what is counter, right? It starts from if you have a counter of 4 digits, which means that it can be 0 0 0 1 or 1 0 and then again 1 1. Okay. So we basically denote this by 0. When you convert it into a binary to a decimal, then it will be 0, then it is 1, then it is 2, and it is. Now they are saying that instead of 0, we are taking it 1 2 3 4 and reset to 1 instead of 0. To solve such a problem, we first identify it's a combinational or sequential logic problem. A clue is to see if we need to remember any previous condition or state, in other words. So like it is going from 1 2 3 4 5 6, hence the circuit clearly is sequential because it has to go sequentially, right? First one will come, then two will come, and three will come, and four will come. It has to go sequentially. So it's a sequential circuit, right? The next step is to identify the states and construct a truth table. From the state, we will give abstraction in binary domain, and we wish to count from, let's say, 0 0 to, let's say, so they have assigned 0 0 to be 1, 0 1 to 2, 1 0 to 3, and 1 1 to 4. Okay, so they assigned, I know this means 0, but they assigned it like that using this sequential circuit. Okay, so they use some kind of a D flip flop. The circuit can be in very state 1 2 3 4, or 4 if the state is 4. 1 2 3 3 here. The next stage should be reset to 1. So when it goes 1 2 3 4, the next state will be 1. Okay, this is how the circuit need to perform. So first we need to make a truth table. Okay, so what we are using is, we are using so the circuit is also given here. What they are asking is, like, using this circuit, uh, you can make this counter using this D flip flops. What will be the gate which will come inside here? Okay, and the truth table is given to you. The present state, which is AB. So what is AB and what is A star AB? So here A is the input to, I think, input to this gate A. is B. Okay, I think am I right? Yeah, so this is present state and this is new state. I think you all heard about this. I think Professor Gandhi has told you. This is D flip flop, right? This is D and this is Q. This is sometimes called. I think yeah, it's a new state. So this is basically called the new state, and this Q is basically called the current or the present state. So this is the present state. This is the new state. The present is this, and when the next clock cycle will come, this state will become this state, right? So something called A star AB is given. Suppose this is D, this Q. Suppose this is A, which is the present state, then this will be A plus. Okay, so this is a simple thing you need to learn. A and A plus. So what you need to do is this is A, okay. This is B, which is the present or the current state, okay. And when you see this, it's the same terminal going to this, and this is B, right? I think this is B. I think this is B. So this B is coming like this, and this is going like this, and this will be A star, the new state, and again this will be a B star. Okay, and you need to find out what will be the gate. Is it XOR gate? So whenever you find this kind of a problem, because truth table is already given to you, okay. So the best way to solve this problem. So like let's say what is this gate will be. I don't know what the gate is, but it is giving A plus, right? And it is giving A and B, right? So how to solve this kind of a problem? One way is to solve is like what we need to solve is take another, let's say A or gate. Then it will be something like I think or will be A plus B, I think. And gate, if you convert it into mathematical one, then it is A dot B. And the other is NOR gate, which is like I think this is NOR. And XOR gate. So A B, this is C option, C option, C option. What you can use is you can use this option sequential manner, and you can do that. And in that manner also you can get an answer. But the other way which you can do is like you can use this formula. So you have this A star, right? This is A star and this is B star. So what you can do is you have this table, right? And if you recollect from the truth table, if the both input is 0 0, you are getting 0. If one of the input is 1, then it is 1. One of the input is 1, then it is 1. If both of them was 1 1 and this is 0, so this is basically the truth table of a XOR gate, okay. I think if you okay, this is basically a truth table of a XOR gate, okay. I don't know if you get it, but you please look into the truth table. I mean, what you can always go is the Google. You can write truth table for boolean. So like for XOR gate like that, and you get some kind of image, like you can see that it is like something like that, like 0 0 1 1 0 0. So it's the same as XOR gate, okay. So how XOR gate looks, I've told you how the, so this is what the XOR gate means, right? A, that's A B star, which like this is XOR gate basically. So your answer will be, I think A, this is A, this is B, this is D, and so your answer will be D here. In that case, okay. So in this manner, you need to kind of think of the problem which you need to think. I know this might be heavy to you because there is a lot more electronics coming, and but you need to bear them. But please, so in the exam we won't ask you many electronics, but the basics like gate and all that you need to know this, okay. Maybe not on the flip flops, but definitely on this architecture type, because this will help you This is the primitive. This is basically the fundamentals of electronics, how to build those circuits and all that. But please do take this question seriously, okay? And yeah, I think this is it. I mean, I think I took like so around 1 hour, 55 minutes. Okay, well, then I will stop recording, and we will meet next week. Till then, bye bye.